The next is the properties of DTFT. So we're going to introduce all these properties. The first one is linearity. When we have these two pairs of DTFT, then linear combination in the time domain corresponds to the same linear combination in the frequency domain, or vice versa. The second one is conjugate symmetry. So when we have this pair of DTFT, the conjugate in the time domain will cause the conjugate in the frequency domain, and also flip of the signal in terms of the vertical axis in the other domain. So this is the other way around. And if the sequence is a real function, then we can further have this valid. Or in other words, the amplitude spectrum will be an even function, while the phase spectrum will be an odd function. Or we can break them into the real part and the imaginary part. Real part will be even, while the imaginary part will be odd. Here is one example. When we have this signal, a non-periodic sequence, what is the amplitude and the phase spectra? So we can use definition to figure out the spectrum. And if we plot the amplitude spectrum, it will be symmetric respect to the vertical axis. And this will be antisymmetric respect to the vertical axis. And these results verified our understanding. When the sequence is a real sequence, then the amplitude is an even function, while the phase spectrum is odd. The third property is shift properties. The first one is time shift. Time shift will cause phase shift in the frequency domain. Time-frequency correspondence. Here is one example. If we have a signal x of k shown in here, what is the spectrum for y of k, which is the time shift for x of k? So here is the time shift version. Without going through the details, we can figure out the spectrum for x of k. Look like this. And when we try to figure out the spectrum, we can simply get the amplitude equal to the spectrum for the x of k. And for this signal, it will have an extra phase spectrum, which is equal to 0 for this sequence. The second shift property is the shift in the frequency domain. So again, the correspondence actually is when you do the shift in the frequency domain, then in the time domain, you're going to have a phase shift. So again, phase shift in the time domain, frequency shift in the frequency domain. Here's one example. If this is the spectrum for this x of k, non-periodic discrete time sequence, what is the spectrum of yk if it is the multiplication of x of k and cosine of pi k? We can use Euler equation to break the cosine function into the summation of two imaginary exponential signals. And the combination of these two terms will be the phase shift in the time domain. So we understand the spectrum of y of k will be the frequency shift of the original signal f of k's spectrum. Or mathematically, it can be written in this format. So if this is the original signal's spectrum, then the phase shift, one is towards your right by pi. Another term is shift to your left by pi. And the combination of these two things divided by 2 will be this waveform in the frequency domain. The next is the convolution properties. So the convolution can happen in the time domain. When you do convolution in the time domain, then in the frequency domain, the operation is multiplication. The second is when you do the convolution in the frequency domain, convolution in the frequency domain corresponds to multiplication in the time domain. So basically, the correspondence is convolution in one domain corresponds to multiplication in the other domain. The next property is differentiation in the frequency domain. This is given DT-FT pair. If we do derivation in the frequency domain, so multiplication in the time domain. The last one is Parseval law. So basically, when we have a pair of DT-FT, the calculation of the energy can be done in the time domain, or it can be done in the frequency domain, and the value got to be the same. And we can try to prove these equations are equal. I'm not going through the details, but with these steps, you should be able to understand how to reach the final conclusion that is given in the Parseval law. And next, we're going to use some examples to show some extra properties for discrete time Fourier transform. So try to evaluate these 4 different definitions. For the first one, we can use the forward discrete time Fourier transform to set capital omega equal to 0. So this part will be equal to 1. So the value of the spectrum when capital omega equal to 0 actually is the summation of the original signal in the time domain. For this value, we can use the same technique. The only difference is the capital omega equal to pi. So this value will be equal to positive 1 or negative 1, depends on k. And here is the results for that value. For the third one, we can again use the definition, but the inverse discrete time Fourier transform. And here we need to set k equal to 0 to set this value equal to 1. And by definition, this value is equal to 2 pi times x of 0. The last one, we can make use of the Parseval law directly to reach the conclusion. Let's summarize discrete time Fourier transform for a non-periodic sequence. A discrete time non-periodic sequence can always be decomposed into a linear combination of imaginary exponential signals. And the coefficients is defined as discrete time Fourier transform. And that spectrum is periodic and continuous. There are a few properties we introduced for DT-FT. They include linearity, conjugate symmetry, time and frequency shift, differentiation in the frequency domain, convolution in the time domain and in the frequency domain, Parseval law for energy calculation. Thank you.